All right, good morning, good afternoon, ladies and gentlemen. Welcome to this series of tutorials. If you haven't already, subscribe to the channel, leave a like, comment, and share. Now, in today's lesson, we are looking at a matrix representation of a linear transformation. So I'm just going to write down an example and we will use that to learn. All right, matrix representation of a linear transformation. Suppose we have a transformation T from the input V onto the output W. So this is representing vectors in V and it is outputting vectors in W. And this linear transformation is defined by T. We can assume that vectors in the input are two-dimensional, meaning that we only have two inputs, x, y. Okay, and maybe the output is three-dimensional. Maybe the output is three-dimensional, so maybe we have 2x, y, maybe x plus y, something like that. So what then is the matrix representation of a linear transformation? Okay, it is very simple. So you need to know that this input has vectors. Okay, we're going to call them Vi, and this output has vectors Wi. Okay, now a matrix representation of a linear transformation is just writing the transformation of the vectors in the input as a linear combination of the vectors in the output, and we find the scalars, and those scalars will represent the transformation. Okay, so let me write it. So we have transformation of vectors in the input as a linear combination alpha I. Remember how we write a linear combination of vectors in the output. Okay, so now we do this for all the vectors in the input and all the vectors in the output. Then we will have a system of equations here. Then this system of equations, we have to solve for alpha I, and the collection of alpha I will form the matrix. As easy as that. So this is the simplest I can explain it. So it's a simple task. We get the vectors in the input, we write them as a linear combination of the vectors in the output. Then we solve for alpha I. Then alpha I will form the matrix representation of the linear transformation. Okay, but how do you know the vectors in the input and the vectors in the output? So most of the times you will be given the vectors in the input. They will specify it, say these are the vectors in the input and these are the vectors in the output. Okay, but if you are not given, then we use what we call usual basis. Okay, usual basis. So whenever you hear the word usual basis, then you know what we're talking about. Okay, so remember, we're looking for the transformation of vectors in the input. We write them as a linear combination of the vectors in the output, and we solve for that. So vectors in the input, suppose we have no vectors in the input, we consider the usual basis. Now the usual basis are these vectors with entries of 1 and the rest of the entries are 0. Okay, so for instance, since we said V, the input is two-dimensional, meaning that we have two components, meaning the usual basis, the first one will have 1, 0, then the second one will have 0, 1, and this will be O. Okay, For a three-dimensional usual basis, as in the vectors in this, so we'll say vectors in W will be three-dimensional, meaning that they need to have three entries. So the first entry is 1, 0, 0. The second one is 0, 1, 0. And the third one is 0, 0, 1. So usual bases are vectors with 1 as the leading variable and the rest of the elements as zeros. So if it was four-dimensional, 4dim, maybe V, if it was four-dimensional, so the vector would be 1, 0, 0, 0, 4 entries. Then the next one is 0, 1, 0, 0. Then the other one will be 0, 0, 1, 0. Then the other one will be 0, 0, 0, 1. So this is the general idea behind usual basis. So if you're not given vectors in the input and vectors in the output, you consider the dimension of the vectors that are supposed to be in the input and the dimension of vectors that are supposed to be in the output. Then you find the usual basis. Okay, so that is the first step. So like we have done here. So since we have seen that the transformation of x comma y is two-dimensional, so we'll use two-dimensional usual basis 1, 0, 0, 1. This is a two-dimensional usual basis. Then since we have 3 dimensions on the output vector W, as we have seen 1, 2, 3, we use a three-dimensional usual basis for vectors in W. Okay, now the next step is writing the vectors in V as a linear combination of the vectors in W. Then we start solving the system of equation. So we write the transformation. We can say this is V1, this is V2, this is W1, this is W1, W2, W3. Okay, so we will write transformation of V1 as a linear combination of alpha 1 W1 plus alpha 2 W2 plus alpha 3 W3. Since there are 3 vectors in the output, then transformation of V2 also as a linear combination of alpha 1 W1 plus alpha 2 W2 plus alpha 3 W3. Okay, so now we will apply the definition. So the definition says for transformation of x comma y, which is equals to 2x, I think that's y, then x plus y. Okay, so we have this. So for V1, this is like x and this is y. Okay, so when we put transformation of x is 1, 0, we know that this will be 1, this would be 0, this is 1 plus 0, 1 plus 0, which is just 1. So what we get as an output is 2, because 2 times 1, then here we have 0, then here we have 1, like that. So this is for t v1, which will be equal to this. Then t v2 will be equal to transformation of, this is v1, so this is v2, this is x and this is y. So we write our x is 0 and our y is 1, so we replace here where there is x, we replace 0, so this is 2 times 0, it should be 0, here it is 1, then here will be 0 plus 1, which is 1. So we have that. Then now we can replace in these equations. So we have this which is this. So it will be 2, 0, 1 be equal to alpha 1. Then W1 is 1, 0, 0. Okay. Plus alpha 2. W2 is 1, 0, 0, 1, 0 plus alpha 3. W3 is 0, 0, 1. Okay, so this is for the first set of equations. For the second one, it is this one. It will be the same, so it will be 0, 1, 1 equal to alpha 1. Then we have 1, 0, 0. Basically the same thing, alpha 2, 1, 0, 1, 0, 0, 1, 0 plus alpha 3, 0, 0, 1. So now we need to solve this system as a system of equations. We'll find alpha 1, alpha 2, alpha 3. That will be the first row. Then this one we solve for alpha 1, alpha 2, alpha 3. That will be the second row. So you've learned already how to solve a system of equations. Okay. For this one, for usual basis, it's usually easy because you have the pivots as the leading diagonal. So basically for this one, this just becomes, since this one alpha 1 times this, it will just be like alpha 1, then everything 0, alpha 2, everything 0, alpha 3, everything is 0. So when you sum this, you just find that you have 2, 0, 1 equal to alpha 1, alpha 2, alpha 3. Okay, but this will not always be the case. But when you're dealing with a usual basis, it will be like that. And you see that alpha 1 is corresponding to 2, alpha 2 is corresponding to 0, alpha 3 is corresponding to 1. So meaning that for the first column, we have 2, 0, 1. Same applies for this. Okay, same applies for this. We have alpha 1, we have 0, 1, 1. But of course, if it was a system of, you have to solve the system of equations. But for usual basis, it makes things easier. So this again will have alpha 1, alpha 2, alpha 3. Okay, but you would have to solve the systems of equations. Then for the solutions, we're going to have 0, 1, 1. Okay, so writing this as a matrix is just this row, this column 0, 1 and 0, 1, 1. Then what we do here is we transpose. So we need to transpose. So the matrix representation equals to 2, 0, 1, 0, 1, 1 transposed. So when we transpose this, we're going to have 2, 0, 1, 0, 1, 1, 1. Okay, so when we transpose that, 0, 1. So this will be the matrix representation of a linear transformation. So let me quickly run through what we've done. Okay, so the journey started here. Suppose we have a transformation V from V onto W, then you'll be given the definition of that transformation. you need to look at, in the definition, this will give away the dimension of the input, and the output gives away the dimension of the output, so that you know. Okay, then it is defined by that, but the transformation, the matrix representation of a linear transformation involves writing vectors in the input as a linear combination of vectors in the output, which is what we've done here. So we write transformation of vectors in the input as a linear combination of vectors in the output. So same procedure. Suppose you're not given vectors in the input and vectors in the output, you consider usual basis, okay? And these are just vectors with the leading element being a 1, and the rest of the entries are zeros. So you consider usual basis. So for 2 dimensions, the usual bases are just 1, 0, and 0, 1. Okay, for 3 dimension, the usual bases are 1, 0, 0, 0. So you just be exchanging the 1, 0, 1, 0, 0, 0, 1. Okay, then you can even think of it as an identity matrix. No, it is 1, 0, 0, 1 for 2 dimensions. And these are these. For 3 dimension, it's 1, 0, 0, 0, 1, 0, 0, 0, 1. And these will be the vectors. You can think of it that way. So, but if you are given vectors, you'll be given the vectors in the input and vectors in the output. Sometimes you just be given the vectors in the input, meaning that vectors in the output, you use the usual basis. If you are given vectors in the output, meaning that the vectors in the input will be used as usual basis. And sometimes if you are not given any of those, you just use usual basis for both. So you name the vectors in the input as v1, v2, and vectors in the output as w1, w2, and w3, whatever you do. Then you write the transformation of vectors in v as a linear combination of vectors in w. Then you solve for alpha I. So you have a system of equation. So here you transform the vectors in the input. So tv1, when we transform that, we get the vector 2, 0, 1. tv2, when we transform the vector, we get 0, 0, 1, 0, 1, 1. Okay, then we replace in the equations. So we have 2, 0, 1 equal to the linear combination that we have. Okay, then we solve for alpha 1, alpha 2. So but if it's a usual basis that you have here, it makes things easier because the individual values of alpha 1, alpha 2 will just correspond to the vectors here. Okay, because when you sum this plus this it will just be alpha 1, and you see that. Okay, so alpha 1 times everything here, it will just be alpha 1, then zeros. Alpha 2 times everything here, it will just be 0, alpha 2, 0. Alpha 3 times everything here, it will just be 0, 0, alpha 3. When you sum that, you're going to have this, and the vectors will correspond to each other, meaning that alpha 1 is equals to that, alpha 2 is equals to that, alpha 3 is equals to that, and so on and so forth. Same applies here. Then you get those values, or let me say the vector of solutions of alpha 1, alpha 2, alpha 3. You write them as a column vector, and you write them as columns of a matrix. So this is for the first one, we write it as a column. Then for the second one, we write it as a column. Then the matrix representation is the transpose of this matrix that we have here. So we have to transpose, always remember that. Okay, so with that being said, one thing that you should be very good at is solving a system of equation. Okay, solving a system of equation. Let me just give another example that you can try out and solve, then we'll see the solution that you have. Suppose, all right, so this is a task that you're going to try out. Suppose the transformation from R3 to R2 is a linear transformation, and it is defined by this. So we have x, y, and z onto 2x plus y and z. So you're going to find the matrix representation for part A let me just write it here. Find matrix representation. Find matrix representation if A, R03 and R2 are spanned by the usual basis, so you know the usual basis of R3 and the usual basis of R2, then this is another example where R3 is spanned by a specific vector, okay, and R2 is spanned by another specific vector. So, but the procedure is just the same. The issue that you just have to deal with is solving a system of linear equations. So you find for the first one, for TV1, you solve. Okay, let me just outline it for the second one, for part B. So for part B, you need to write the vectors in R3 as a linear combination of vectors in R2. So something like that. Okay. So you transform the vectors in R3 and you write them as a linear combination of vectors in R2. All right. So maybe this is V1, this is V2, this is V3. Okay. Maybe this is W1 and this is W2. Okay. So writing the transformation of V1 as a linear combination of alpha 1 W1 plus alpha 2 W2, since there are only two vectors here, so you go again T V2 equals to alpha 1 W1 plus alpha 2 W2, transform TV3 equals to alpha 1 W1 plus alpha 2 W2. So from this set, you will find vectors alpha 1 and alpha 2. From here, you find the answers for alpha 1, alpha 2. From here, you find values of alpha 1, alpha 2. Then you write these as column vectors. So the first part will be this one. You write it like that. Then the second column will be this one. You write it there. Then the third column will be this one. You write it like that. Then you have some form of alpha 1 for this part, then alpha 1, alpha 2, alpha 1, alpha 2 from this part, then the other alpha 1, alpha 2 from the other part. Then you have to transpose this, and that will be your matrix representation of a linear transformation. So for this one, you solve alpha 1 and alpha 2, so it will be a system of linear equations. Simple. Even for this one, you solve, then you form that matrix. As easy as that. So you can pause through, run through the video again and again. Yeah, and all the best. So one more time. So after you write this, for this one, you will solve the system of equations for alpha 1, alpha 2. That will make the first column. For this one, you solve for alpha 1, alpha 2. We make the second column. For this one, you solve for alpha 1, alpha 2. You have the third column. Then you transpose that. And that will be your matrix representation of a linear transformation. And that's it for today. So I hope you have a great day. And remember, you will be solving a system of equations. So the system can have infinitely many solutions. The system can have no solutions, meaning that it is not possible to find the matrix representation of a linear transformation. So all those things that you know about systems of equations, the system can have infinitely many solutions, no solution, or there could be a unique solution. So if we have a unique solution, then we have a simple matrix representation of a linear transformation. If we have infinitely many solutions, then we're going to have some scalars representing pivots. Okay, so if we have no solution, then we are dealing with a transformation that cannot be represented as a matrix representation. So that's it for today. Have a great day.